Hello JPG Discovery followers. We all learn about the three states of matter early on, solid, liquid, and gas. But there's a fourth state, often overlooked but far more prevalent. This state, plasma, dominates the universe. So what exactly is plasma? Imagine heating a gas to extreme temperatures. As the heat intensifies, the atoms within the gas become energized. Electrons, those tiny particles orbiting the atom's nucleus, gain enough energy to break free. This separation creates a mixture of free-floating electrons and ions, atoms that have lost or gained electrons. This ionized gas is what we call plasma. Unlike ordinary gases, plasmas possess unique characteristics. The presence of free-moving charged particles makes plasma electrically conductive. It also responds strongly to electromagnetic fields, behaving in ways that solids, liquids, and gases cannot. While plasma might seem exotic, it's all around us. Lightning bolts crackling through the sky, the neon glow of advertising signs, even the flame of a candle. These are all examples of plasma at work. Creating plasma requires energy, often a considerable amount. One way to do this is by heating a gas. As the temperature rises, the gas atoms collide with increasing force. These high-energy collisions eventually strip electrons from the atoms, forming plasma. Plasma also forms through other processes, like the passage of an electric current through a gas. This is how fluorescent lights generate their characteristic glow. Electricity flowing through the gas excites the atoms, causing them to release photons of light and form a plasma. However, the most dramatic examples of plasma formation occur naturally in the vast expanse of space. Stars, those celestial giants, are essentially enormous balls of plasma. Within their cores, immense pressure and temperatures reaching millions of degrees create the perfect conditions for plasma to exist. Plasma isn't just a scientific curiosity. It's the most abundant form of visible matter in the universe. While it might seem scarce on Earth, venture beyond our planet, and you'll find plasma everywhere you look. Stars, as we mentioned, are primarily composed of plasma. Our own sun, a rather average star, is a churning ball of hot plasma, fueled by nuclear fusion reactions deep within its core. But it's not just stars. The vast spaces between stars, known as the interstellar medium, are also filled with plasma, albeit at much lower densities. This interstellar plasma, while incredibly thin, plays a crucial role in the evolution of galaxies and the formation of new stars. Explaining from cool to blazing, the range of plasma exists across an incredible temperature range. When we think of plasma, we often imagine the searing heat of the sun. While it's true that some plasmas reach millions or even billions of degrees, others are surprisingly cool. High-temperature plasmas, like those found in stars, are incredibly energetic. The atoms and electrons within these plasmas move at incredible speeds, constantly colliding and releasing energy. These plasmas emit intense radiation, including visible light and X-rays. On the other end of the spectrum are low-temperature plasmas. These plasmas, also known as cold plasmas, exist at temperatures closer to room temperature or even lower. While they might not be as visually spectacular as their high-temperature counterparts, cold plasmas have numerous technological applications, from etching circuits on computer chips to sterilizing medical equipment. Example, our stellar furnace, the Sun's plasma heart. The Sun, our very own star, provides a spectacular example of plasma in action. Deep within its core, temperatures soar to millions of degrees and pressures are immense. Under these extreme conditions, hydrogen atoms, stripped of their electrons, fuse together to form helium, releasing a tremendous amount of energy in the process. This energy, in the form of light and heat, radiates outward from the Sun's core, eventually reaching Earth and sustaining life on our planet. But the Sun's plasma doesn't just stay put, it also streams outward into space, forming what we call the solar wind. Explaining solar winds and earthly lights. The solar wind is a constant stream of charged particles, primarily protons and electrons, flowing from the Sun's upper atmosphere or corona into space. This plasma wind carries with it the Sun's magnetic field, influencing the entire solar system. As the solar wind reaches Earth, it interacts with our planet's magnetic field, creating a spectacular light show known as the Aurora Borealis, or Northern Lights, and Aurora Australis, or Southern Lights. These shimmering curtains of light occur when charged particles from the solar wind collide with atoms in Earth's atmosphere, exciting them and causing them to emit light. But the solar wind isn't always so benign. Intense bursts of solar wind, known as solar storms, can disrupt satellites, communication systems, and even power grids on Earth. Understanding and predicting space weather, driven by the sun's plasma activity, is crucial for protecting our technology-dependent world. The secrets of plasma. Plasma, while ubiquitous in the universe, remains a subject of intense scientific study. Unlocking the secrets of plasma physics has far-reaching implications, from harnessing fusion energy here on Earth to understanding the dynamics of distant galaxies. Scientists are working to recreate the conditions of the sun's core in laboratories, aiming to achieve controlled fusion reactions. If successful, fusion power could provide a clean and nearly limitless source of energy for future generations. By studying plasma in space and in the laboratory, we are constantly refining our understanding of this fascinating state of matter. Plasma physics holds the key to unlocking many of the universe's mysteries, from the birth of stars to the evolution of galaxies. As we continue to explore the cosmos, one thing is clear: plasma, the universe's hidden powerhouse, will continue to shape the universe as we know it.